We agreed on getting them.
You wake up, post up, round in it, flossing on it. This diamond, my diamond. This rock, my rock. I woke up like this.
Hardy.
Weinberg.
Hardy Weinberg. Our equation can be used to test
Whether population is evolving in just one equation.
Our principle states that frequencies of alleles and genotypes in a population remain constant from generation to generation.
population. A population is a group of individuals that line in the same area and interbreed, producing fertile offspring.
We can characterize a population's genetic makeup by describing its gene pool.
Gene pool?
She's thinking of a pool full of genes. How cute is that?
So cute. No, a gene pool consists of all alleles in a population, silly.
Yep, and a locus is fixed if our population are homozygous for the same allele. The frequency of an allele in a population can be calculated.
There are two alleles at a locus. The letters P
And Q
are used to represent their frequency. Together, they equal to 1!
Now, P plus Q is equal to 1.
Let's say we have a population of goldfish. We're going to look at one phenotype. They're colored.
One is yellow and one is green. Which one's dominant?
The yellow is dominant to the green.
Yep, the frequency of the yellow goldfish is dominant to the green, which represents our variable P. Q represents the green goldfish for the frequency of the recessive allele. We're going to use big Y for yellow and little y for green. So if we take a small sample of our fish population, we have a homozygous dominant, another homozygous dominant, a heterozygous for the yellow goldfish, and a homozygous recessive. What is P and what is Q in our gene pool? Well, we would solve this simply by counting up the big Y alleles out of the total number in our gene pool of 8 alleles, which gives us 0.625 for P. There are two ways to find Q. You can either count the little y's, 3 out of 8, or simply subtract 0.625 from 1 and you get 0.375. Well, that was pretty straightforward, but it gets a little bit more complicated when we go to the equation describing the individual population's genotypes. So we're looking for genotype frequency, and that means 2 alleles. Allele number 1, P plus Q equals 1, and allele number 2, P plus Q equals 1. Genotype is allele number 1 and allele number 2, which means you multiply. If both of those equal to 1, then hey, foil! First, outer, inner, last. Which gets us to our Hardy-Weinberg equilibrium. P squared plus 2pq plus q squared equals 1. P squared is the frequency of homozygous dominant genotype, or big Y. 2pq is the frequency of the heterozygous genotype, or big Y little y, and q squared is the frequency of the homozygous recessive genotype, or little y.
This accounts for the homozygous recessive. Okay?
So for example, in the goldfish population, 0.16 or 16% are green. What is the frequency of big Y little y? Well, we know that 0.16 is q squared, because that is your homozygous recessive, and take the square root of both sides and you get 0.4 for q. Now going back to the first of the Hardy-Weinberg equations, P plus Q equals 1, so P plus 0.4 equals 1 is 0.6. Now that we know P and Q, we can figure out the frequency for big Y, little y, which is heterozygous, which represents 2pq from the equation. So 2 times 0.6 times 0.4 will get you 0.48. So roughly half of the population is heterozygous. They are still yellow, but they are actually carrying that little y, but it's recessive, so they don't show it. The gene pool is modified if mutations alter alleles or if entire genes are deleted or duplicated. If individuals mate preferentially within a subset of the population, such as their close relatives, inbreeding, random mixing of gametes does not occur and genotype frequencies change. Differences in the survival and reproductive success of individuals carrying different genotypes can alter allele frequencies. Charles Darwin would be like, seriously? The smaller the population, the more likely it is that allele frequencies will fluctuate by chance from one generation to the next, a process called genetic drift. By moving alleles into or out of the populations, gene flow can alter allele frequencies. Let us apply a principle in estimating the percentage of a population carrying the allele for phenylketonuria. I'm just going to say PKU for short. It is a metabolic disorder that results from homozygosity for a recessive allele, which, if you remember, represents Q squared. Left untreated, PKU results in mental disability and other problems. We can assume the gene mutation rate is low and the mate selection is random, and the rest of the reasonable assumptions hold. The occurrence of PKU is 1 out of 10,000 births, which represent Q squared for the frequency of the homozygotes, which is 0.001. Square both sides to get Q and you get 0.01. Now using the gene pool equation, the frequency of normal or dominant alleles represent P, which is 0.99. And then to find the frequency of carriers or heterozygotes, use 2pq from the genotype equation and plug that in, and you get 0.0198, which rounds to 0.02, which means approximately 2% of the U.S. population does not have PKU, but may pass the PKU allele to offspring. Remember, the assumption of Hardy-Weinberg equilibrium yields an approximation. The real number of carriers may differ. Still, our calculations suggest that harmful recessive alleles at this and other loci can be concealed in a population because they are carried by healthy heterozygotes.
Oh, I get it now.
Good job, Hardy. Good job, Weinberg.
See you out that door, baby. Bye, bye, bye.